There used to be a sound that televisions made when they had nothing to show you. A grey blizzard on the screen, a flat hiss out of the speaker. The noise a machine makes when it is listening as hard as it can and hearing nothing in particular, except that it was hearing something. Most of that snow came from the ordinary world, the warmth of the ground, the electronics in the room, the atmosphere overhead, the sun when it was up. But a portion of it arrived from considerably further away, and nobody can say exactly what portion. The precise sounding figures in circulation are estimates passed between writers rather than anything anyone measured. Call it a small fraction. That fraction left its source 380,000 years after the beginning of the universe, travelled for 13.8 billion years without striking anything at all, and ended its journey as a fleck of grey on a screen in somebody's living room. It did not stop when the analog signal did. Roughly 400 of those photons occupy every cubic centimetre of the air in this room, which means that in the volume your body takes up, something close to 27 million of them are inside you right now. They are travelling at the speed of light, so they are also leaving. The entire population is replaced completely about 200 million times every second. They arrive from every direction at once, and they arrive from a wall. Not the edge of the universe. The universe may not have one. This is a boundary of a different kind, the point past which light carries nothing further back, because further back than that there was no light able to travel freely. It surrounds this room at a distance nothing could cross, and its centre is wherever you happen to be sitting. It has a name, and it is the least evocative name ever attached to anything this important: the cosmic microwave background. What it is, underneath the name, is the moment the universe became transparent. For the first 380,000 years, there was no such thing as a clear line of sight. Everything was hot enough to be a plasma. Atoms could not hold together, electrons ran loose, and light could not get more than a short distance before something knocked it sideways. The universe was not dark in that era. It was blindingly bright and completely opaque, which are not the same condition at all. Then it cooled past a particular threshold. The electrons settled onto the nuclei, the fog lifted, and the light was released in every direction at once. That release is what is still arriving. It is the oldest thing any instrument has ever detected. Nearly everything we now know about the universe as a whole came out of that noise. The age, 13.8 billion years, is measured from it. We have that number to within about 20 million years, which sounds like a catastrophic margin until the proportion is worked out. It is the equivalent of knowing the length of a human life to within 2 months. The shape of space came from it as well. Whether the universe curves the way the surface of a sphere curves, or whether two parallel lines stay parallel forever, was an open question for most of the 20th century, and it was closed by measuring a pattern in this light. As far as anyone can tell, space is flat. And then the inventory. Every star, every planet, every atom in every living thing that has ever existed, all of it together, comes to about 1/20th of what the universe contains. The rest is dark matter and dark energy, and we named them both after our own ignorance. The difficulty was never the measurement. 4 separate people measured this light before anyone understood what they were holding. An astronomer in Canada in 1941, reading it out of the behavior of a few molecules drifting between the stars. 2 more in the 1950s in different countries, both looking for something else entirely. And an engineer at Bell Telephone Laboratories in New Jersey in 1961, who found it with the very same antenna that would make 2 other men famous 4 years later. He wrote the number down in a report and went back to his work on satellite telephones. 24 years passed between the first measurement and the moment somebody understood it. The signal was never hiding. It falls on every square meter of this planet in daylight and in darkness, and it was doing so long before there was a planet for it to fall on. What was missing was not the data, it was the question. The question is the recent part. This light has been crossing the universe for 13.8 billion years, arriving everywhere, continuously, from every direction, past stars and through dust and rock and water and the dark. For almost the whole of that journey, it arrived in rooms with nobody in them. It fell on a planet that could not feel it, and then on oceans, and then on things swimming in those oceans, and none of them knew. Only very recently did it begin falling on something that could ask where it came from. The light did not change. The room did. Before we go back, and we are going back a long way tonight, first to a hillside observatory in the winter of 1941, and then very much further, to a universe with no darkness in it at all. One small thing. If these documentaries are part of how the night gets through, subscribing helps more than it probably should. It is most of the mechanism by which quiet things find the people who want them. And if there is still enough waking left, leave a comment with the place you are listening from and the time it is there. There is something steadying about the shape of that. The same voice arriving in a bedroom in Manila at 4 in the morning, and a kitchen in Rotterdam near midnight, and a parked car in Arizona at the end of a long shift. Say what brought anyone here tonight, if the mood takes you. People arrive at the cosmic microwave background from surprisingly strange directions. Now, 1941. An observatory on a hill above Victoria, British Columbia, and an astronomer named Andrew McKellar working through somebody else's photographs of somebody else's star, noticing that a scatter of molecules drifting in the space in front of it were very slightly warmer than they had any right to be. They had been taken years earlier and half a continent away, at Mount Wilson in California, by an astronomer named Walter Adams, who had spent much of his career photographing the spectra of hot young stars and depositing the results in the scientific literature like a man patiently filling a warehouse. One of those plates recorded the light of a hot blue star in the constellation of the Serpent Bearer. Adams was interested in the star. What lay between it and his telescope was, for his purposes, an obstruction. Starlight does not reach us untouched. On the way, it passes through enormous thin drifts of gas, and the atoms and molecules loitering in those drifts absorb particular wavelengths as the light goes by, so that what finally arrives at the telescope is a spectrum with pieces missing, a smooth band of color interrupted by narrow dark lines, each one the signature of something the light had to get past. Most astronomers of the period read those lines as contamination. McKellar read them as information about the space itself. Among them were several belonging to cyanogen, a molecule of one carbon atom bonded to one nitrogen atom, common enough between the stars and, as it happens, an unusually good thermometer. A cyanogen molecule can spin, and like almost everything at that scale, it cannot spin at just any rate. It is restricted to a ladder of specific speeds with nothing permitted in between. A molecule resting on the bottom rung, not spinning at all, absorbs light at one precise wavelength. A molecule that has been nudged up to the first spinning state absorbs at a slightly different one. Both sets of lines show up on the plate, and the relative darkness of the two tells you what fraction of the molecules out there are turning. Something has to be doing the nudging. In interstellar space, the gas is so thin that collisions are almost unimaginably rare, and a molecule can drift for centuries without meeting another one, which leaves very little available to spin it up except light. So the fraction that are turning is a direct reading of how much radiation soaks the space they inhabit, and from that fraction, you can work out a temperature. McKellar worked it out. The answer was 2.3 degrees above absolute zero. That figure deserves a moment. Absolute zero is the floor, the point at which there is no heat remaining to remove, 273 degrees below the freezing point of water. What he was reporting is that the space between the stars, out where there is essentially nothing at all, sits a little over 2 degrees above that floor, colder than anywhere on the surface of this planet has ever been, and yet not cold enough. Something out there was keeping it warm. He published the result, and he hedged it. The rotational temperature, he wrote, had a very restricted meaning, by which he meant that it described the behavior of certain molecules in one particular direction, and that nobody should inflate it into a grander claim. He was doing precisely what you are supposed to do, and he was also, without knowing it, declining the largest claim available to anyone that century. Because the number was right. The temperature of the space between the stars as we measure it now is 2.725 degrees above absolute zero. Makella's 2.3, extracted in 1941 from the spin rates of molecules on somebody else's photographic plates, is closer to that value than the measurement that would win the Nobel Prize 24 years later. The most accurate early reading of the oldest light in the universe was taken by a man who did not believe he had measured anything of consequence. The molecules have not stopped spinning, incidentally, and the method is still in use. Cyanogen remains one of the ways the temperature of the sky gets checked, and because the same trick works on gas clouds far enough away that their light has been traveling for billions of years, it has since been used to demonstrate that the universe really was warmer in the past. You could go and take that measurement tonight, given a large enough telescope. It would confirm him. 7 years later, on the other side of the continent, a graduate student was working out what the early universe would have had to be like. Ralph Alpha was completing a doctorate under George Gamow, and the problem in front of him was the origin of the chemical elements. If everything had begun hot and dense, then the first minutes would have been a nuclear furnace, and the proportions of hydrogen and helium in the universe today ought to be the ash left behind. Alpha pushed the calculation through, and it worked as far as it went. The theory produced hydrogen and helium in roughly the observed amounts, then stalled, unable to build its way past the lightest elements into anything heavier. Gamow, whose sense of humor occasionally outran his judgment, added Hans Bether's name to the resulting paper so the author list would read Alpha, Bether, Gamow. Bether had not worked on it. The joke has outlasted almost everything else about the episode, and it had the incidental effect of burying a doctoral student's work beneath two of the most famous names in physics. The prediction itself came later that year in a letter Alpha wrote with Robert Herman, dated the 25th of October and published in Nature 3 weeks afterwards. If the universe had once been that hot, they argued, it had been drowning in radiation, and radiation does not simply disappear. It would have been stretched and cooled by the expansion ever since, but it would still be here, filling everything, at a temperature they put at around 5 degrees above absolute zero. In a single short letter, they had described the thing Makela had already measured. Neither of them knew. Nobody told them, because nobody had noticed there was anything to tell. It is worth being fair about why that prediction failed to detonate. It did not stay still, for one thing. Over the following years, the estimate wandered upward and outward, running as high as 50 degrees at various points as the assumptions and input data shifted underneath it. For another, the two men never proposed that anybody go and look. They had produced a number rather than an experiment, and in physics, those are very different objects. And the prediction was bolted to a theory that had visibly run into a wall over the heavier elements, so anyone inclined to dismiss the nucleosynthesis program was liable to sweep the radiation out along with it. Then, twice in the 1950s, the radio astronomers found it. In 1955, working at a wavelength of about 1/3 of a meter, an astronomer named Leroux recorded a signal that was the same in every direction he pointed, 3 degrees. 2 years later, at a much shorter wavelength of a little over 3 centimeters, Shmounov recorded 4. Both are, in retrospect, detections, Neither was at the time a discovery, and the reason is written into the numbers themselves. Leroux's 3 degrees carried an uncertainty of ±2, meaning the true value might have been anywhere between 1 and 5. Smirnov's 4 carried ±3. A measurement with error bars that wide is not a result but a suggestion, and it was a suggestion offered in a young field where every receiver had its own unexplained warmth, and the standard assumption about unexplained warmth was that you had built the thing badly. So by the end of 1957, the published record stood like this. A prediction existed in one of the most widely read journals in the world that the universe should be filled with radiation at a few degrees above absolute zero. 3 separate measurements existed in 3 separate literatures of radiation filling the universe at a few degrees above absolute zero. They sat in the same libraries, sometimes on the same shelves, and for 17 years they did not touch. They did not touch because they were written in different languages. McKellar's result belonged to molecular spectroscopy. Alpha and Hermann's belonged to nuclear physics. Leroux's and Smirnov's belonged to radio engineering. Those communities read different journals, went to different meetings, and had no particular reason to suspect that a paper on the spin states of cyanogen had anything to say to a paper on the manufacture of helium. Specialization is what lets science go deep. It is also, with great reliability, what lets an answer sit unclaimed in plain view for the better part of 2 decades. What finally broke the pattern was a piece of hardware. 20 feet of aluminium, shaped like an enormous squared-off ear, standing on a low hill in New Jersey and built for the wholly unrelated business of bouncing telephone calls off a balloon in orbit. 3 men would read the same excess warmth out of it. 2 of them would go to Stockholm. The one who did not go to Stockholm was named Ed Ohm, and he found it 3 years before the others did. Ohm was an engineer doing an engineer's job. In 1961, he was characterizing the receiver on that antenna so that Bell Labs would know precisely how much noise stood between a satellite and a telephone call. Every component in a chain like that contributes a little warmth of its own: the atmosphere, the waveguide, the amplifier, the ground leaking in around the edges. And the procedure is to add up everything that can be accounted for and compare the total against what the instrument actually reports. The 2 numbers should agree. Ohm's did not. There were about 3 degrees more arriving than anything in his accounting could explain, and he published the figure as a line item inside a paper about a satellite receiver and left it there. He did not pursue it, and it is worth understanding why. An unexplained few degrees in a noise budget is an untidy entry when you are trying to close a radio link to an object in orbit. It is not a research program. Ohm had a deadline and a system to deliver, and he delivered it, which is awkward for the explanation that covers all the earlier misses. The measurements of the 40s and 50s went unclaimed because they were scattered across communities that did not read one another's journals. That defense does not survive Holmdel. Ohm's number and the number that would become famous came out of the same instrument, in the same building, taken by colleagues at the same laboratory 3 years apart. Nothing separated them except what each man decided to do about a discrepancy he could not explain. The antenna had been built for Project Echo, which remains one of the stranger ideas the early space program ever committed to hardware. A balloon 100 feet across, made of metallized plastic, inflated in orbit, off which radio signals could be bounced from one side of a continent to the other. There was no equipment aboard. The balloon was a mirror and nothing else, which meant the signal coming back down had spread across thousands of kilometers of sky, glanced off a sheet of plastic and spread out all over again, so that what reached New Jersey was a whisper of the whisper it had set out as. Later, the same horn tracked Telstar, which at least carried its own transmitter. To hear any of that, Bell Labs built a receiver of extraordinary sensitivity and hung it on an antenna shaped to reject everything it was not aimed at. That shape matters more than it sounds. A conventional dish scoops up stray warmth from the ground around its rim, whereas a horn reflector is shielded along its whole length, so that when you point it somewhere, you are genuinely listening only to that place. The instrument had been designed to be certain about where its signals were coming from. Nothing in that design was intended for cosmology, and all of it turned out to be exactly what cosmology needed. By 1964, the satellite work had moved on and the horn was free. Arno Penzias and Robert Wilson wanted it for radio astronomy, a discipline with an unforgiving relationship to noise, because in astronomy, the faint signal is not an obstacle to the work. It is the work, and nobody can claim a detection until every degree of warmth in the equipment itself has been accounted for. So they calibrated. The method was to hold the sky up against a reference of known temperature, in their case a load cooled with liquid helium and sitting a little over 4 degrees above absolute zero, which is about as cold as anything on this planet gets without considerable effort. They aimed the antenna upward, switched across to the reference, and compared. The sky was too warm by 3.5 degrees that would not fit anywhere in the accounting. What followed was 10 months of trying to make it go away. The first suspect is always the instrument, because the first suspect should always be the instrument. When a machine hands you a number, nothing explains. The overwhelmingly probable answer is that you built it wrong, and the professional response is to assume exactly that until you can prove otherwise. They checked the joints and the amplifier, rebuilt what could be rebuilt, remeasured what could be remeasured, and the 3.5 degrees sat precisely where it had been. Then they went after the sky, and the signal began giving itself away by refusing to behave like anything local. It did not change when they moved the antenna. Warmth leaking up from the ground would have risen as they tilted towards the horizon and fallen as they aimed at the zenith, and it did neither. It read the same overhead, the same at an angle, the same wherever they put it, and a source that gives an identical reading in every direction is a source with no location, while every explanation then available required the noise to be coming from somewhere in particular. It did not change with the hour. Anything driven by the sun would have swung through a daily cycle, and anything generated by people, whether a city or a road or a transmitter, would have carried some rhythm of human activity in it. This had none. It was as strong at 3 in the morning as at noon. It did not change with the season. They watched it from July of 1964 through to April of the following year, across the humidity of a New Jersey summer and the dry cold of the winter behind it, and the atmosphere's own emission differs considerably between those two conditions. The excess did not shift, and it carried no polarization. That one is quieter than the others and may be the most damning of them. A great deal of what a radio telescope hears arrives with a preferred orientation. Electrons spiraling through the galaxy's magnetic field emit light with a twist in it, and reflected signals tend to be polarized as well. This had no twist at all. Something unpolarized, arriving from every direction, at all hours and in all weather, is not the signature of anything happening. It is the signature of something simply being warm. There remained the horn itself, and inside the horn there were pigeons. A pair had settled in the narrow throat of the antenna, where the structure funnels down towards the receiver, and they had been in residence long enough to coat the surfaces. Penzias, writing about it afterwards, called the deposit a white dielectric material, and the phrase has trailed the story ever since. It was not a joke when he wrote it. A dielectric layer is a real suspect. Anything sitting at ordinary room temperature, around 300 degrees above absolute zero, radiating gently into a receiver built to register a few, is exactly the sort of thing that can manufacture an excess out of nothing at all. So the birds were removed. They were caught, crated, and sent to the Bell Labs site at Whippany, some distance inland, where they were let go. Homing pigeons do what homing pigeons do. They were back in the throat of the antenna within days, and the second time they were caught, they were shot. The horn was taken apart as far as it could be taken apart, the throat was scrubbed clean, and the whole assembly was reassembled. Penzias and Wilson aimed it at the sky and measured again. 3.5 degrees. That is how the discovery was actually made, by systematically running out of ways to be wrong about it. The word discovery implies a moment of arrival, and there was no moment. There was most of a year of methodical subtraction, at the end of which a number was left standing with nowhere to hide, and 2 men who had exhausted their reasons for disbelieving their own equipment. Ed Ohm had held that number 3 years earlier and had not been wrong about anything. He measured accurately, reported honestly, and drew no conclusion, because drawing conclusions was not the task in front of him. Penzias and Wilson had no such task either. Nothing whatsoever obliged them to spend 10 months on 3.5 degrees. They could have folded it into an error budget, published their astronomy, and moved on, and nobody would ever have known there had been anything to find. By the spring of 1965, they had eliminated the ground, the sun, the galaxy, the atmosphere, their own equipment, and the birds. And what survived all that subtraction was a warmth with no source, no direction, and no schedule, filling the sky wherever they aimed. They still had no idea what it was. And 50 kilometers down the road, in a laboratory at Princeton, 4 men were at that moment assembling an instrument for the express purpose of finding the very thing that Penzias and Wilson had spent 10 months trying to get rid of. The theory that sent them looking is one almost nobody believes anymore. It's supposed that the universe does not have a beginning so much as a rhythm, that it expands, slows, falls back on itself, collapses to a density and a temperature nothing can survive, and then rebounds and starts over. No first moment and no last one. An enormous breathing, running forever in both directions. Robert Dick found the idea attractive, and he noticed a problem with it. If every cycle inherits the wreckage of the one before, the universe ought to be getting dirtier. Stars manufacture heavy elements out of hydrogen and scatter them across space when they die. And if that debris simply accumulated from one pass to the next, then after an unlimited number of passes, there would be no hydrogen left anywhere. Nothing to build new stars from, and no way for any cycle to resemble its predecessor. For the rhythm to keep working, something has to clear the table between rounds. The only candidate is heat. If the collapse became hot enough, every heavy nucleus assembled by every star of the previous cycle would be broken back down into hydrogen, and the next expansion would begin with a clean sheet. What Dickey was describing was a universe that periodically incinerates its own chemistry and returns it to the simplest thing there is, which meant there had to be radiation left over. You cannot heat a universe to the temperature required to take iron apart and then expect the heat to quietly disappear. It goes into light, and that light stays, stretching and cooling as the expansion resumes. Somewhere out there, thinned and chilled by however long it had been traveling, the remains of the last fire ought to still be detectable. He was unusually well placed to go and look because he had spent the war building precisely the instrument the job required. Dicker was a theorist who worked with his hands, a rarer combination than it sounds. At the radiation laboratory in wartime Massachusetts, he had designed a microwave receiver that solved the central obstacle to measuring anything faint, which is that a receiver's own wandering warmth drowns out whatever it is trying to hear. His solution was to make the instrument flick rapidly back and forth between the sky and a reference held at a known temperature, so that what it reported was a difference rather than an absolute value, and the slow drifts cancelled themselves out. The design is still called a Dickey radiometer. He had built the tool 20 years before he thought of the thing to aim it at. So he assembled a group. James Peebles, then a young theorist, took the calculations. How hot, how long ago, and what temperature the remnant should have cooled to by now. Peter Roll and David Wilkinson took the hardware and began building a radiometer on the Princeton campus to go and find it. None of them knew that any of this had been done before. Alpha and Herman's letter had been sitting in nature for 16 years, and Dickie had never encountered it, and neither had anybody else in the room. 4 men were rediscovering from scratch a prediction that was already in the published record, and doing it, this time, with an experiment attached to it. They were perhaps 6 months away from a working instrument when the telephone rang. Word had travelled to Penzias by the indirect route such things usually take. A conversation with a colleague, a mention of a preprint circulating out of Princeton, a suggestion that the person worth calling might be Dickie. Penzias picked up the telephone and called him, and described an antenna standing in a field at Holmdel, 10 months of elimination, and 3.5 degrees of warmth that refused to go anywhere. Dicker listened. Peebles, Roll and Wilkinson were in the room, hearing one side of it. A man saying very little and asking short questions. When he put the receiver down, he turned to them and said, "Boys, we've been scooped." 6 months was the entire margin. 17 years had passed since a prediction had been published that nobody followed up, and after all that stillness, 2 groups converged on the same object within half a year of each other, neither aware the other existed until somebody made a phone call. What Dickie did next receives the least attention of anything in the story, and may be the most creditable part of it. He did not dispute the measurement, and he did not rush to publish ahead of it. He arranged for the 2 to appear together. They ran in the Astrophysical Journal on the 1st of July, 1965, in the same issue, one directly after the other. Dickie, Peebles, Roll and Wilkinson came first, under the title Cosmic Black Body Radiation, setting out what a hot, early universe would leave behind and why a few degrees of uniform warmth was exactly the residue to expect from it. Penzias and Wilson followed, under the title A Measurement of Excess Antenna Temperature at 4,080 megacycles per second. The 2 letters share a page. The one that explains what the thing is ends on the same sheet where the one that found it begins. Set the 2 titles beside each other and you can read the whole situation off a couple of lines of type. One of them names the origin of the universe. The other names a calibration problem. And the second letter never closes that distance. Penzias and Wilson's paper runs to about 2.5 pages, and it does not mention the Big Bang. It does not mention the early universe, or cosmology, or what any of it might imply about anything. It reports a measurement, describes the checks, gives the number, and observes that a possible explanation for the observed excess is offered in the accompanying letter, which is to say they gestured at the pages above theirs and declined to add a word. There is a version of that restraint which is timidity and a version which is discipline, and this is the second. They had measured 3.5 degrees. They had not measured the beginning of the universe. What you are entitled to publish is what you have actually established, so they published that and stopped. It is the same instinct that made McKellar qualify his molecules in 1941, and there it cost him everything, because in 1941 nobody was standing by to supply the meaning. This time somebody was, 5 pages earlier, in the same issue. Before that issue went to press, the question of how the universe began was a question a person could hold opinions about. Well-informed, professionally serious people held opposite views, and no measurement existed that could separate them. Afterwards, one did. Whatever else those few pages accomplished, they moved the origin of everything out of the category of things that get argued and into the category of things that get measured, and it has remained there since. The argument they settled had been running since 1948, which happens to be the year Alpha and Herman published their letter, and for most of the 17 years in between, the losing side had been a perfectly respectable place to stand. Its chief architect held an intense dislike of the notion that the universe possessed a first moment, and it was he who had given the winning theory the name it carries to this day. On the 28th of March, 1949, a British astronomer sat down in front of a microphone at the BBC and, in the middle of explaining why he thought a rival cosmology was mistaken, reached for a phrase. "These theories," he said, "were based on the hypothesis that all the matter in the universe was created in one big bang at a particular time in the remote past." Fred Hoyle was not coining a name. He was assembling a picture in ordinary words for people listening to the radio in their kitchens, and the phrase he used was lowercase and descriptive and meant to be forgotten by the end of the sentence. Other people turned it into a title. That slightly reframes the question everyone asks about it. The familiar version says Hoyle meant the words as ridicule, and it is easy to see why that reading has stuck, since he was arguing against the theory at the time and went on arguing against it for the rest of his life. But Hoyle himself denied any mockery, insisting he had only been trying to build something a listener could hold on to, and there is no way now to establish what was in his head on a March evening in a broadcasting studio. What is not in dispute is the outcome. The name fastened itself to the theory he opposed, outlived his objection, and is still the name. It is also, as names go, a bad one. It suggests an explosion, which implies a center, a shock wave, and somewhere for the debris to fly outward into, and the event it describes had none of those. There was no outside. It did not happen anywhere in particular, because everywhere was inside it. The winning theory of 20th century cosmology carries a label supplied by its chief opponent that is also misleading in nearly every detail, and nobody has ever succeeded in replacing it. The theory Hoyle was defending had been published the year before by Hermann Bondi and Thomas Gold, with Hoyle arriving at a version of his own by a separate route. Its founding move was a sort of principled stubbornness. Astronomers had already accepted that the universe looks broadly the same in every direction, with no special place and no privileged corner. Bondi and Gold extended the courtesy to time. If no place is special, they argued, then no moment should be special either, and a universe that looks the same everywhere ought to look the same at every epoch as well. The obstacle is that the universe is expanding, and an expanding universe holding a fixed quantity of matter thins out. To keep the appearance constant, matter has to be created continuously, new hydrogen appearing in the gaps at precisely the rate required to hold the density steady. This sounds outrageous, and it was, but the arithmetic is what made it survivable. The rate needed came to roughly 1 atom of hydrogen per cubic meter of space per billion years, which sits so far beneath any conceivable measurement that no experiment could ever catch the universe in the act. Depending on your temperament, that was either the theory's elegance or its escape hatch. It also disposed of a problem that was, at the time, acutely embarrassing. The expansion rate had been measured badly, and running it backwards produced a universe roughly 2 billion years old, while geologists dating rocks by radioactive decay were confidently reporting terrestrial minerals older than that. Anyone holding a theory with a beginning had to explain how the Earth had contrived to be older than the universe it sat in. A theory without a beginning was untroubled because in it the universe has always been here, and the age of any particular stone is nobody's difficulty. By the late 50s, the position was deteriorating. Martin Ryle's group at Cambridge had been counting radio sources across the sky and sorting them by brightness, on the reasoning that fainter sources lie generally further away and are therefore seen further back in time. If the universe truly looked identical at all epochs, those counts should have followed one specific pattern. They followed a different one. There appeared to have been more powerful radio sources in the distant past than there are nearby today, which is exactly what a changing universe produces and exactly what a steady state forbids. Hoyle disputed the counts publicly and at length, and the exchanges grew genuinely unpleasant, and the data kept accumulating in the same direction. Then came 3.5 degrees. The difficulty it created runs deep. Radiation with a thermal character, the sort that arises from something merely being warm rather than from any particular process, is produced when matter and light sit together long enough and densely enough to settle into balance with one another. That requires an era in which everything, everywhere, was compressed and hot. An evolving universe has such an era built into it. That era is what the theory is about. A steady-state universe, by its own definition, has never had one, because if things had ever been denser, then the universe would have looked different then, and looking the same always is the whole premise. So the radiation had to be manufactured some other way, and the only raw material on offer was starlight. Stars have been burning forever in that picture, and their output has to go somewhere. Absorbed by dust spread through intergalactic space and re-radiated at longer wavelengths, perhaps it could add up to a background. The proposal has a structural flaw that no amount of adjustment removes. Starlight comes out of stars, stars sit in galaxies, and galaxies are strewn through space in clumps, so a sky lit by reprocessed starlight ought to be brighter where the galaxies are and dimmer where they are not. What had been found at Holmdel read the same everywhere it was aimed. Smoothing that out requires dust of a very particular composition, distributed with a very particular uniformity, radiating at a very particular temperature. And every one of those particulars is a number chosen after the fact to match a measurement you already have. The observation did not so much refute the steady state as remove the ground it had been standing on. A theory can survive an awkward result. What it struggles to survive is being obliged to invent new machinery every time somebody measures something. Hoyle never accepted it. He spent the following decades building variants and rescues, and the rescues grew more elaborate as the evidence grew heavier, until he was arguing from a position almost nobody else occupied, which is a peculiar fate for a man whose best work had been to fill in the largest hole in his opponent's theory. The early universe calculations could manufacture hydrogen and helium, and then stopped, unable to climb to anything heavier. It was Hoyle, working with Willie Fowler and with Geoffrey and Margaret Burbidge, who established where the rest of the periodic table actually comes from, forged inside stars across billions of years and thrown outward when those stars die. The carbon in a living body and the oxygen in a breath are accounted for by a paper published in 1957 by 4 people, one of whom did not believe in the Big Bang and never would. The Nobel Prize in Physics for 1978 was divided. Half went to Piotr Kapitsa for his work in low-temperature physics. The other half went jointly to Arno Penzias and Robert Wilson for their discovery of cosmic microwave background radiation. Dickey was not on the citation. 2 explanations circulate, and neither has ever been resolved. One holds that the prediction had already been made in 1948 and that Dicker had simply never encountered it, which makes his contribution a rediscovery. The other holds that the committee was unenthusiastic about an alternative theory of gravitation Dicker had developed and marked him down for it. Both may be partly true, neither may be. There is a plainer reading available, which is that the prize did precisely what it advertises. It is awarded for discovery, and if you take that word strictly, the people who discovered the radiation are the 2 who measured it. Dickey's group explained what it was, and explanation is not discovery under the rules as they are written, and the rules as they are written produced a result that has looked slightly wrong to almost everybody ever since. Alpha and Hermann, who had put the prediction in print 17 years before anyone stumbled into it, never received a Nobel Prize at all. Neither did Hoyle, whose work on the origin of the elements was honoured in 1983, when Fowler was given the prize and Hoyle was not. One of the 4 names on the Princeton paper would receive one eventually. It would take 54 years. What survived all of it, the broadcast, the counts, the argument, the citations, was the number. 3.5 degrees is not a temperature anything chooses. It is what is left of something enormously hotter once sufficient time has passed, and so the question stopped being whether the warmth was real and became how hot it had been and how long ago, and what state the universe must have been in to leave behind a residue of exactly that size. The way to find out is to run the whole thing backwards, and the procedure is less exotic than it sounds. Space is expanding, which is a measured fact rather than a philosophical position, and one consequence is that light stretches while it travels. A wave crossing an expanding room comes out longer than it went in, and stretching a wave lowers its energy, and lowering the energy of the light that fills a volume lowers its temperature. So the further back the film is wound, the smaller the universe becomes, and the hotter its radiation gets, in strict proportion. Halve the size, double the temperature. There is nothing subtle about it. Matter behaves similarly, and slightly differently. Squeeze a fixed quantity of matter into a smaller volume, and its density climbs exactly as fast as the volume falls. Radiation loses twice over, because it is not only crowded into less space, but individually stretched as well, which means that going forwards it thins out faster than matter does, and going backwards it gains. There was a long early stretch during which the universe carried more energy in light than in everything else put together. Wind the film back far enough and you reach a period when every cubic meter of the universe, everywhere, without exception, sat at roughly the temperature of the surface of the sun, not near a star, not in some favored location. All of space at close to 6,000 degrees, with nowhere cooler to retreat to, because there was no elsewhere for the heat to drain into. Keep going and it climbs steeply. At an age of 1 second, the whole thing stood at something like 10 billion degrees. At those temperatures, atoms are not available. An atom is a nucleus with electrons held onto it, and that grip is not especially strong. Heat it sufficiently, and the electrons are knocked loose faster than they can settle. So the early universe contained no atoms. What it contained were the components, bare nuclei, mostly hydrogen with some helium, a sea of free electrons moving among them, and light packed into every gap between them. The free electrons are the difficulty, and they are the reason for everything that followed. An electron on its own is remarkably good at intercepting light. A photon passing close to one is not swallowed, it is deflected, sent off in a new direction with its energy essentially unchanged, in a process named after J.J. Thomson. Each collision leaves the photon intact and pointing somewhere else. Do that once and nothing much has occurred. Do it relentlessly in a medium crowded with free electrons, and light stops traveling in any meaningful sense of the word. It still moves at the speed of light between collisions, but the collisions arrive so frequently that its direction is scrambled before any real distance has been covered. The photon staggers. It goes a short way, turns, goes a short way, turns again, and the net progress across all those steps amounts to a small fraction of the total distance walked. The average length of a single step is what physicists call the mean free path. And in the early universe it was very short indeed. The nearest thing to that condition still running today is the inside of a star. Light generated in the core of the sun does not simply fly out into space. It scatters endlessly off the charged particles packed into that interior, working its way outward by staggering rather than by traveling, and it takes many thousands of years to reach the surface. The distance it is attempting to cross, the radius of the sun, is about 2 seconds at the speed of light. 2 seconds of distance and thousands of years of journey. The comparison sharpens against something else. Neutrinos are produced in that same core by the same reactions, and because they barely interact with matter at all, they come straight out. They cross the Sun in a little over 2 seconds and arrive here 8 minutes later. Same origin, same distance, and one of them takes millennia, while the other takes seconds. The only difference between them is how often they get stopped. There is no honest way to place a person inside the early universe, since a person is assembled from atoms and atoms could not exist there. But suppose, impossibly, that you could stand in it and look around. The experience would be a uniform glare with no features in it of any kind. Seeing requires more than the presence of light. It requires light that has arrived from a particular direction, carrying information about where it has been, and every photon arriving at the eye would have been turned so many times, so recently, that it would retain no memory of any source whatsoever. It would arrive from every direction at once, at identical brightness. There would be no shadows, because a shadow requires light coming preferentially from one side. There would be no shapes, no edges, no horizon, nothing near and nothing far. You could hold a hand up in front of your face and it would simply fail to appear, because the hand and the space beside it would be precisely equally bright. This is what fog does, on a far smaller scale and at a far lower temperature. Fog scatters, and scattering destroys direction, and once direction has gone, vision goes with it. The whole universe sat in that condition, glowing, for a very long time. There is a second consequence of all that scattering, and it matters considerably more than the blindness. Because the photons kept colliding with the electrons, and because the electrons were bound to the protons by electrical attraction, all three were effectively bolted together and could not move independently. Push the matter and the light traveled with it. Compress the light and the matter came along. For those first hundreds of thousands of years, the universe behaved as a single substance rather than as matter and radiation kept in separate accounts. That substance had two properties which do not often turn up together. It had mass, so gravity acted on it, and wherever the density ran slightly above average, the excess drew more material inward. It also had enormous pressure, because compressing light is like compressing a spring, and the harder it is squeezed, the harder it pushes back. Anything possessing both mass and stiffness, once it has been disturbed, moves in a particular way and keeps moving. And whatever it happened to be doing at the instant the coupling broke would be frozen exactly as it stood and left behind. All of this held until the temperature dropped far enough for the electrons to be captured, at which point the scattering stopped and everything changed. The obvious question is when and if you work it out the obvious way you land on an answer wrong by a factor of more than 50. Removing the electron from a hydrogen atom takes a specific amount of energy, and that energy corresponds to a temperature of close to 160,000 degrees. Above that, atoms are dismantled as fast as they assemble. Below it, in principle, they should hold together. A straightforward reading of the physics says the universe ought to have cleared while it was still at something near 160,000 degrees, early and hot and long before anything else of interest had happened. It did not. The electrons stayed loose all the way down to 3,000 degrees, more than 50 times cooler than they had any business remaining loose at, and the delay ran on for hundreds of thousands of years. Whatever kept them from settling is the same fact that explains why there is so much of this light and so little of everything else. Count the photons in a given volume of space, then count the atoms in the same volume, and the ratio between the two comes out at roughly 1.6 billion to 1. That proportion is not an accident of the present day. Photons and atoms both thin out as the universe expands, and although the light loses energy along the way, it is not destroyed, so their numbers relative to one another have stayed essentially fixed since the first few minutes. Whatever the ratio is now is what it has always been. There is a way to feel the size of it. 1.6 billion is close to the number of seconds in 50 years. So for every single atom of ordinary matter in existence, every proton, every hydrogen nucleus that would one day find its way into a star or a planet or into you, there is one photon for every second of a 50-year life. By simple head count, the universe is overwhelmingly light, with matter suspended in it at a rate of about 1 particle per 1.5 billion, which is what kept the electrons loose. The naive calculation asks whether the average photon carries enough energy to strip an electron from a hydrogen atom, and it answers that below 160,000 degrees it does not. The answer is correct, and it is also beside the point, because radiation at a given temperature is not made of photons that all carry the same energy. Most cluster near the average. Some carry rather more. A very small number carry a great deal more, and the population thins out steeply towards the higher energies, but it never quite ends. So the question that actually governs the timing is a different one. Whether there are still, somewhere up in that thinning tail, more atom-breaking photons than there are atoms available to break. With 1.5 billion photons standing behind every atom, the answer remains yes for an extraordinarily long time. Only one photon in 1.5 billion needs to be carrying enough. The tail has to be pushed down by a factor of billions before the supply of destructive photons finally drops below the supply of hydrogen, and pushing an exponential tail down by a factor of billions demands an enormous amount of cooling. 50-fold, as it turned out. The energy required is not a cosmological quantity, incidentally. It is a property of hydrogen measured on laboratory benches with spectrographs, and it is the same in a glass tube in a basement as it was everywhere in the universe 100,000 years in. The timetable of the early cosmos was set by a number you can look up. There is a further complication, and it is the reason the change took as long as it did. When a free electron falls onto a proton and drops directly into the lowest available state, it releases precisely the energy it had to shed, which is precisely the energy needed to ionize a hydrogen atom. The photon it emits travels a short distance into the surrounding gas and dismantles the atom next door. Direct recombination is self-cancelling. For every atom it builds, it breaks another. The universe had to find a slower road, and it did. Electrons could work their way down through intermediate steps and reach the bottom by an unusual and inefficient route that releases 2 feeble photons rather than one dangerous one, and neither of the two is capable of ionizing anything at all. The path works. It is also slow, and its slowness set the pace of the entire transition. Working out how the process actually proceeds was a substantial piece of physics in its own right, published in 1968 by James Peebles, 3 years after the discovery he had helped to explain. At 3,000 degrees, the balance finally tipped. Electrons settled onto nuclei and stayed there. The free charges vanished out of the gas, and light that had spent hundreds of thousands of years being turned aside every few moments abruptly found nothing in its way. What was released at that instant was not faint. 3,000 degrees is close to the temperature of the filament in an old-fashioned incandescent bulb, and the color is the same. A warm orange-white, its peak sitting just beyond the red end of what a human eye can register. The whole universe glowed that color, not a lamp burning in a room, but every cubic meter of everything, in every direction, with no shadow anywhere and no place darker than any other. Then the expansion carried on, and the glow kept stretching, and it has been stretching ever since. The date of all this is worth putting into proportion because the raw figure is deceptive. Recombination finished around 380,000 years after the beginning, and 380,000 years sounds like an era. Compress the entire history of the universe into a single year, with the beginning at midnight on the 1st of January and this present moment at midnight on the 31st of December. On that scale, the Sun and the Earth do not turn up until the start of September. Everything ever written down by anybody occupies the final dozen seconds before the year runs out. The whole opaque era, all of it, every one of those hundreds of thousands of years in which nothing anywhere could see anything, ends at 14 minutes and 28 seconds past midnight on the 1st of January. The universe has been transparent for the other 99.997% of its life. There is a name for the boundary this creates, and the name is slightly misleading. It is called the surface of last scattering, after the moment each photon was deflected for the final time before starting its uninterrupted journey. But it is not a surface in the sense of a place. It is a moment, and the geometry that follows from that deserves care. Light takes time to cross distance, so looking outward is also looking backward, and the further out the gaze reaches, the earlier the epoch it lands on. Look far enough in any direction, and you arrive at the instant the universe cleared. That instant happened everywhere at once, which puts it at the same distance in every direction, which makes it a sphere, and the sphere is centered on the observer, for the simple reason that the observer is the one point from which all those distances come out equal. Everyone anywhere gets one. A creature in a galaxy on the far side of the observable universe has its own sphere, assembled from entirely different photons released by entirely different material. The two spheres overlap, and neither contains the other. There is no single shared wall out there that everybody is looking at from different angles. There are as many walls as there are places to stand, nor is the surface thin. Recombination could not complete in an instant because of that slow and awkward path the electrons were forced to take, and so the release was smeared across tens of thousands of years. The resulting shell runs roughly 30 million light-years deep. What reaches us is therefore not a photograph of a single moment, but a long exposure taken across a slab of time, its finest details softened by the sheer duration of the event that made them. The light that left that shell is the light still arriving. It set out at 3,000 degrees, the color of a burning filament, and it lands here a little under 3 degrees above absolute zero, far outside anything an eye can detect. Down in the microwave band, its wavelengths pulled longer by a factor of about 1100 on the way. Everything the universe did across 13.8 billion years is recorded in the gap between those two ends of the journey, and the measurement of exactly how far it fell turned out to be among the most precise things anyone has ever done. The remarkable thing about the journey that follows is the absence of events. It leaves the last electron that will ever touch it and travels. Space expands beneath it, so its wavelength lengthens in step, but nothing intercepts it, nothing absorbs it, nothing changes its direction. It passes through regions that will condense into galaxies and regions that will empty into voids, and neither of them lays a finger on it. Across 13.8 billion years, essentially the only thing that occurs to that photon is the stretching of the space it is crossing. That absence of events is what makes the whole enterprise possible. The information the light was carrying when it left has not been overwritten, because there was nothing out there to overwrite it with. The geometry of the trip, though, is strange enough to be worth slowing down over. When that photon set out, the material that released it was around 40 million light-years away from the material that would eventually become this planet. Not a vast separation by the standards of what came later. The photon then took 13.8 billion years to cover it. Both of those statements are correct, and the reconciliation is that the gap kept opening while the light was inside it. Every meter of space between the 2 points was itself expanding, so the distance being crossed grew faster than a single crossing could keep up with for a long stretch of the journey. And by the time the photon arrived, the material that emitted it had been carried out to a present separation of roughly 45.7 billion light-years. So the surface of last scattering sits at about 45.7 billion light-years. The furthest anything can be seen at all lies a little beyond that, at around 46.5 billion, and the observable universe measures something like 93 billion light-years across, despite being under 14 billion years old. None of that is a contradiction. It is what happens when the thing carrying the light and the thing being measured are the same substance. What arrived, when it finally arrived, had a very particular shape, and that shape is the reason any of this counts as evidence. Any warm object emits light across a spread of wavelengths, and for most objects, the spread is untidy. Chemistry intervenes. A cloud of gas emits fiercely at the specific wavelengths its atoms favor, and hardly at all in between. A solid surface reflects some colors and absorbs others. Real things carry the fingerprints of what they are made of. There is one exception, and it is a strict one. When matter and radiation are locked together and left to exchange energy long enough, the light forgets everything about its source and settles into a distribution governed by a single quantity, not mainly governed, solely. Give it a temperature and you can write down the entire curve, the brightness at every wavelength from one end of the spectrum to the other, with no adjustable parameters and no room to negotiate. It is called a blackbody spectrum, and the striking thing about it is how little freedom it has. Two black bodies at the same temperature are identical, regardless of whether one was a lump of iron and the other a universe. Producing that shape requires exactly the conditions described earlier. Matter and light so densely packed and so persistently colliding that every trace of origin is scrubbed out of the radiation. Which means the spectrum is not merely consistent with the fog, it is a receipt for it. It is also extremely fragile in one specific way. Once the light is free, anything that dumps energy into it afterwards leaves a mark. Particles decaying, early stars igniting, gas heating up along the way. Any of it would push some part of the curve away from the ideal shape and leave a bump or a dip that no temperature could account for. The perfection of the spectrum is therefore a constraint on the entire history of the universe since the fog cleared. So the measurement mattered enormously, and the measurement was hard, because the atmosphere sits directly on top of the wavelengths involved and glows in them. The Cosmic Background Explorer launched on the 18th of November 1989, carrying 3 instruments. 1. The diffuse infrared background experiment, hunted for the accumulated glow of the earliest galaxies. Another, a set of differential microwave radiometers, was there to look for structure in the light, a question that would take a further 3 years to answer. The third was the far infrared absolute spectrophotometer, run by John Mather, and its assignment was the shape of the curve. Its method was the old one. Rather than attempting an absolute reading, it compared the sky against a reference held on board, an engineered blackbody cooled with liquid helium, built to be as close to ideal as human manufacturing could manage, and reported the difference between the two. Point the instrument at the calibrator, then at the sky, and measure the gap. The gap was almost nothing. Across a span of wavelengths covering nearly a factor of 10, the sky matched a blackbody curve with deviations smaller than 50 parts in a million of the peak brightness. That number resists intuition, so here is a way to hold it. 50 parts per million is 5 centimeters of error along a ruler a kilometer long. Or more usefully, when the FIRAS measurement is drawn on a graph, the uncertainties are around 100 times thinner than the line used to plot them. You cannot draw the error bars at all, because at any sensible scale they are narrower than ink. The best reference blackbody that could be constructed on Earth was held up against the sky, and the sky was at least as good. That remains the situation. The most perfect example of thermal radiation anyone has ever encountered was not manufactured in a laboratory, and it is not a curiosity in a vacuum chamber. It fills everything. The temperature that came out of it, refined over the following 2 decades, and settled in a 2009 analysis combining every precision measurement available, is 2.725 degrees above absolute zero, pinned down to within roughly 6/10,000ths of a degree. That is a precision of about 2 parts in 10,000. The temperature of the entire universe is known more exactly than you know the temperature of the room you are sitting in, and it is the same in every direction to a degree of sameness that took a satellite above the atmosphere to establish, which makes the very first thing anyone notices when they go hunting for structure in that uniformity faintly comic. One half of the sky reads measurably warmer than the other, by a margin roughly 100 times larger than any other variation in the map, and it says nothing at all about the early universe. It is there because we are moving. Penzias and Wilson reported that their excess was identical in every direction, and they were right at the precision available to them. The variation that dominates every modern map of the sky amounts to about 1 part in 800 of the total signal. Their instrument was hunting for a discrepancy of a few whole degrees against a reference bath of liquid helium. A difference of 3/1000ths of a degree between one side of the sky and the other was not something that antenna could have registered under any circumstances. The uniformity they observed was real uniformity, measured honestly at the resolution they had. Better instruments arrived and the uniformity came apart, which is what usually happens. The definitive measurement came in the 1970s, and it required getting above most of the atmosphere. A group from Berkeley, including a young experimentalist named George Smoot, mounted a differential radiometer in a U-2, an aircraft designed for high-altitude reconnaissance, and flew it repeatedly at the edge of the stratosphere, swinging the instrument from one side of the sky to the other and reading off the difference. The pattern they found was unambiguous. The shape of it follows from something ordinary. Move towards a source of light and its waves arrive compressed, which registers as bluer and hotter. Move away and they arrive stretched, which registers as redder and cooler. The unusual part here is that the light is not coming from a source. It is a bath, filling the whole of space, arriving from everywhere at once. Move through a bath like that and no single object's color shifts. The entire hemisphere ahead warms and the entire hemisphere behind cools, with a smooth gradient running between the two. That is what the sky does. There is a hottest point, and directly opposite it, a coldest point, and the temperature slides evenly from one to the other across the intervening 180 degrees. The difference between the two extremes comes to roughly 7/1000ths of a degree, 3 1/3 above the average in front, the same amount below it behind. Run that backwards through the Doppler arithmetic and it gives a speed. The solar system is traveling at 369 kilometers per second relative to the radiation, which is 1 1/3 million kilometers per hour. The Earth's orbit around the Sun, a motion nobody thinks of as slow, runs at about 30 kilometers a second. So this is more than 12 times faster than the speed that carries this planet around its star. You are doing it now and have been doing it your entire life, along with every object in this room, and there is no sensation attached to it whatsoever, because uniform motion has no sensation attached to it. The only reason anybody knows is that the oldest light in the universe is very slightly warmer in one direction than the other. That figure is a sum, and taking it apart is worth the trouble. The Earth goes around the Sun at 30 kilometers a second. The Sun goes around the center of the Milky Way at something near 230, completing a circuit roughly every 250 million years. The Milky Way moves within the small collection of galaxies it belongs to, and that whole collection is itself traveling. These do not simply add because they point in different directions. At this stage of the Sun's galactic orbit, our rotation around the center of the Milky Way is aimed roughly against the direction the larger group is heading, so it partly cancels. The result is that our personal velocity relative to the radiation is smaller than our galaxy groups. In something over 100 million years, when the Sun has carried us round to the far side of its orbit, the two motions will point the same way instead, and the number will be considerably larger. Whatever that speed happens to be, it is not a permanent property. It is a stage in a rotation. Strip out the local motions and the underlying figure is the important one. The local group, the Milky Way, Andromeda, and the several dozen smaller galaxies bound up with them, is moving at around 627 kilometers a second in a direction that lies towards the constellations Hydra and Centaurus. Something is pulling. In 1988, a group led by Donald Lynden Bell put a name and a location on it, calling it the Great Attractor and placing it a couple of 100 million light-years off in that direction. The name has stuck, though the picture has since become less tidy. The pull appears to come from an extended concentration of mass rather than one object, with further large structures lying beyond it in the same line contributing their own share. The awkward part is that the direction sits close to the plane of our own galaxy. Looking that way means looking through the full thickness of the Milky Way, through its stars, its gas, and above all its dust, which absorbs visible light thoroughly enough that a substantial band of sky has historically been almost unmappable. We are falling towards something we cannot see properly, and the obstruction is not distance or darkness. It is the galaxy we happen to live inside. There is a question this raises which deserves a straight answer because it sounds like it should be a problem. If the radiation defines a state of rest and our motion relative to that state is measurable, has something gone wrong with relativity? A preferred frame is exactly what relativity is supposed to forbid. Nothing has gone wrong. What relativity forbids is a frame in which the laws of physics take a different form, a way of establishing absolute motion by experiment, without reference to anything outside your laboratory. That remains impossible. Every experiment performed inside a sealed room moving smoothly through the universe returns the same results as one performed in a room at rest. The dipole is not that. It is a measurement of motion relative to something, and the something is the contents of the universe. Sit in a still room and the air around you defines a frame. Run across it and you feel wind on your face. Nobody regards that as a crisis for physics because the air is simply stuff with an average velocity, and moving relative to stuff is detectable. The radiation is the same case, with one addition that makes it far more useful. It is the only stuff that is everywhere. There is a frame at every point in space in which the universe looks the same in all directions, and it is the frame in which the whole history of the expansion is described most simply, and the light is what lets anybody identify it locally. It does not give a center. It gives every observer, everywhere, a way of asking how fast they are drifting with respect to the average. Take that pattern out, model it, measure it, subtract it, and the sky settles back into the flatness described earlier, and the map is finally clean enough to be asked the question it was built for. What lies underneath is 100 times fainter than the motion that had been sitting on top of it, and it is the first thing in the whole of this story that has nothing to do with us. The argument that something had to be down there begins from a fact nobody disputes. Galaxies exist. A galaxy is a region where matter has collected. It got that way through gravity, which pulls harder wherever there is already more material, drawing in still more and deepening the imbalance as it goes. The process is relentless once it starts, and given enough time, it will turn a slightly denser patch of gas into a star, a cluster, a spiral, 100,000 light-years across. But gravity only amplifies differences that already exist. It has no capacity to manufacture them. Drop it into a universe of perfectly uniform density and you get nothing at all, because every particle is pulled equally in every direction and there is no reason for anything to move. A perfectly smooth universe stays perfectly smooth forever. So the material at last scattering cannot have been smooth. Some regions must have been marginally denser than others, and denser regions sit at the bottom of deeper gravitational wells, and a photon climbing out of a deeper well loses a fraction of its energy on the way. It arrives fractionally cooler, which means the temperature of the sky has to vary from place to place, tracing the pattern of density that existed at the moment the light was let go. That much was understood long before anyone had the instruments. The open question was the amplitude, and for 2 decades the answer was smaller than we can measure. Through the 1970s and 80s, group after group went looking. Balloons, mountaintops, ground stations, aircraft. Every one of them came back with an upper limit rather than a detection, and every limit was lower than the last, and each new failure made the situation worse rather than better. Structure needs time to grow. Start with variations that are too shallow, and gravity simply cannot deepen them into galaxies within the age of the universe. By the late 80s, the permitted range had been squeezed down towards a level where the ordinary picture of how galaxies form began to look impossible. The escape route from that problem is worth understanding because it turned a failure into evidence. Ordinary matter in that era was bolted to the light. Push a clump of it inward and the radiation trapped alongside pushes straight back out, so density variations in ordinary matter could not deepen at all while the coupling lasted. They were held flat by pressure for the entire opaque period, and only began to collapse once the light let go of them. Dark matter has no such handicap. Whatever it is, it does not interact with light, so radiation pressure has no grip on it whatsoever. Its density variations were free to grow from very much earlier, quietly, invisibly, while the ordinary matter was still being held in place. By the time the fog cleared, there were already deep wells waiting, dug by something that had never been slowed down, and the ordinary matter dropped into them at once, which means the ripples in the light are allowed to be far shallower than they would otherwise need to be, because the structure they seeded had received a substantial head start from material that leaves no imprint on the light at all. The smallness of the temperature variations is not an embarrassment. It is one of the sturdier arguments that most of the matter in the universe is of a kind nobody has ever handled. Finding them was a problem of engineering. The instrument was the second of the 3 carried by the Cosmic Background Explorer, a set of differential microwave radiometers, and it worked on the principle that had been standard in the field since the war. Rather than attempting an absolute temperature for any patch of sky, it carried 2 horns pointed 60 degrees apart and reported only the difference between them, sweeping across the sky as the spacecraft rotated and building the map out of comparisons. It observed at 3 separate frequencies, roughly 31, 53 and 90 gigahertz, and the reason for that is the Milky Way. Our own galaxy glows in the microwave band, from electrons spiraling in its magnetic fields, from warm dust, from ionized gas, and that glow sits directly on top of the signal. What separates them is color. The relic light is a black body, so the ratio of its brightness between any 2 frequencies is fixed and known exactly. Galactic emission follows entirely different rules. Measure at 3 frequencies instead of 1, and the 2 can be told apart and the foreground stripped away. The resolution was coarse. Each beam took in a patch of sky about 7 degrees across, which is 14 times the width of the full moon, so anything smaller than that was smeared into an average. The map that resulted could only show the very largest features, the broadest, gentlest undulations, with everything fine-grained blurred out of existence. The announcement came in April of 1992, and it rested on a single year of observation. The team had sat on the result for a long time first, running the analysis against itself because the signal was so faint that the difference between a discovery and a systematic error was not obvious from the inside. The variations came in at roughly 1 part in 100,000. Taken at the very largest scale on the sky, the amplitude was 13 millionths of a degree, give or take 4. 13 millionths. Set beside a background temperature already less than 3 degrees above the coldest possible temperature there is. To get a sense of the flatness involved, if the surface of the Earth were smooth to that standard, the tallest thing you could climb would stand about 64 meters high, a 20-story building, and that would be the summit of the world. Everest overshoots it by a factor of nearly 140. That is the roughness of the early universe. Everything that has been built since was built out of that. George Smoot led the team that found it, which makes his career a fairly tidy arc. The man who measured our own motion from the back of a reconnaissance aircraft went on to strip that motion out and find what had been hiding underneath it. He shared the 2006 Nobel Prize in Physics with John Mather, whose instrument had established the shape of the curve on the same spacecraft. Smoot died in Paris in September of 2025 at the age of 80. 13 millionths of a degree is a variation so slight that calling it faint is generous, and it is the reason there is anything whatsoever in the sky above you. What nobody could say from a map that course was where the pattern had come from, or why it had the particular size it did, or what had been happening in that fluid during the hundreds of thousands of years before the light was released. Those answers were sitting in the fine structure, in everything smaller than 14 moons across, which was precisely what the instrument had been unable to see. What came after the clearing was darkness, and it lasted a very long time. The glow released at recombination went on stretching and cooling, sliding down out of the visible range within a few million years, and once it had gone, there was nothing else. No stars had formed. Nothing anywhere was burning. The universe at that stage held hydrogen, a quantity of helium, whatever dark matter is, and a fading warmth that had already dropped below anything you could have seen. And it stayed in that condition for something on the order of 100 million years, expanding quietly in the dark. Which is the period the whole pattern had to survive, and the reason it did is that gravity does not require light in order to work. The wells were already dug. Dark matter had spent the opaque era assembling them, unimpeded, and the temperature variations in the released light are a map of where they lay. Once the ordinary gas was no longer held flat by radiation pressure, it began to drain into them. The process is not dramatic. A region carrying slightly more mass than average pulls slightly harder on its surroundings, which means it expands slightly more slowly than the universe around it, which means it falls progressively further behind the general thinning out, which means its density relative to everything else climbs. The climb is slow and it compounds, the way arithmetic compounds, and across tens of millions of years a difference of 1 part in 100,000 becomes 1 part in 1,000, and then 1 part in 10, and eventually the region stops expanding altogether and begins to fall inward on itself. Falling gas heats up. Compression does that. Squeeze any gas and you raise its temperature. And in the center of a collapsing cloud, the density and the temperature climb together until hydrogen nuclei are being driven into one another hard enough to fuse. That is a star, and the first ones were unlike anything burning now. Star formation today is helped along by heavy elements, which radiate away heat efficiently and let a collapsing cloud shed energy and fragment into many small pieces. The first clouds had no heavy elements because nothing had yet made any. Hydrogen and helium are poor at getting rid of heat, so the clouds resisted breaking up, and what condensed out of them is thought to have been enormous. Stars of tens or hundreds of times the Sun's mass. burning at temperatures nothing has matched since. Objects that size do not last. The Sun will spend roughly 10 billion years on its main sequence. A star 100 times heavier consumes its fuel in 2 or 3 million, which is around 1,000th of that. They lit up, they burned ferociously, and they died almost immediately on any cosmic reckoning. Nobody has seen one. This is the least directly observed link in the entire chain, inferred from physics rather than photographed. And the James Webb Space Telescope has been steadily pushing the observational frontier back towards the era in question, finding galaxies already assembled earlier than most models expected. The first individual stars themselves remain beyond reach. What they did while they burned is the part that matters here. Fusion in a massive star works upward through the elements. Hydrogen becomes helium. Helium becomes carbon and oxygen. Then, as the core contracts and heats between stages, neon, magnesium, silicon, sulfur, each stage faster than the last, each releasing less energy than the one before, the final stages taking days rather than millennia. The sequence terminates at iron. Fusing anything lighter than iron releases energy. Fusing iron itself consumes energy instead. A core that has reached iron has nothing left to burn, and with nothing generating pressure, the core collapses in under a second, and the outer layers of the star fall onto it and rebound. The explosion that follows throws everything the star manufactured out into the surrounding gas, and in the extremity of the blast, and in collisions between the dense remnants such stars leave behind, elements heavier than iron get assembled as well. The gold, the iodine, the uranium. Then it happens again. The enriched gas cools, gathers into new wells, and forms a second generation of stars, now with carbon and oxygen available to help it cool and fragment. So this time, the stars come out smaller and more numerous and longer-lived. Those in turn die and enrich further. The concentration of heavy elements in the galaxy climbs, generation over generation, and somewhere along the way it crosses the level at which rock can condense out of a disk of gas and planets become possible. The Sun assembled itself about 4.5 billion years ago out of material that had already been through several rounds of that cycle. The Earth condensed from the same cloud, and its iron sank to the center, and its silicates floated, and the residue of all of it is what everything here is built from. Some specifics are worth stating precisely, because the chain is exact rather than poetic. Roughly 10% of your body's mass is hydrogen, and effectively, every one of those atoms was assembled in the first few minutes of the universe. They predate every star that has ever existed. They are the oldest objects you will ever handle, and there are more of them in a body than atoms of any other kind. The oxygen, around 65% by mass, most of it locked into water, was made inside stars. So was the carbon, at about 18%, and the nitrogen in every protein, and the calcium in bone, and the phosphorus holding the strands of genetic material together. And in your blood there are about 4 grams of iron, most of it sitting at the center of hemoglobin molecules, where it binds oxygen and lets it go again with every breath. Every atom of it was manufactured in the last hours of a star's life and blown outward by the explosion that ended it long before the Sun existed. All of that is what the pattern did once it was released. What set it going in the first place left no mark on the broad, shallow undulations a 7-degree beam could record, because those were simply the largest and smoothest things in the sky. The evidence lay at scales far below anything yet measured. When instruments sharp enough to reach them were finally built and flown, the shape they found there was the shape of something ringing. Sound is a pressure wave moving through a medium. That is the entire definition, and it makes no reference to air or to ears or to any particular range of frequencies. Compress part of a substance that resists being compressed, let go, and the disturbance travels. Whether you are present to hear it is a separate question and not a physical one. The early universe had a medium, and it had something to disturb it, and what followed was sound in the strict and technical sense of the word, rather than as a figure of speech. The mechanism turns on a difference in what gravity is allowed to do, depending on which side of recombination you look at. Afterwards, gravity operates unopposed. A region carrying more mass than average draws in more material, and nothing pushes back, and the collapse runs to completion. Beforehand, the same region behaves entirely differently, because the material it is pulling on is the coupled fluid rather than plain gas. Gravity drags the mixture inward. The light inside it, compressed, pushes outward harder and harder as the squeezing continues until the outward pressure overwhelms the inward pull and the region begins to expand again. It does not settle politely at the point where the two balance. It arrives there moving, carries straight through, and keeps expanding until it has become less dense than its surroundings, at which point gravity, having lost the argument, wins it back, and the region begins to fall inward once more. That is an oscillation. The same lump of extra density that would simply collapse in the later universe instead sat there ringing in and out for as long as the coupling held. The speed at which those waves traveled is worth stopping on. The speed of sound in any medium is set by how stiff it is against how heavy it is, and the stiffness in this case came almost entirely from radiation, which is extraordinarily resistant to being compressed. That pushes the sound speed up to a shade under 60% of the speed of light. Sound in air moves at about 1/3 of a kilometer per second. Sound in the early universe moved at something like 170,000 kilometers per second, roughly 500,000 times faster than the fastest sound anyone has ever heard. Even at that speed, the waves could not go far, because there had not been much time. A disturbance beginning at the very start could travel outwards for the whole age of the universe up to that point and no further, and the distance it covered sets a hard ceiling on the size of any structure the process could produce. It is called the sound horizon, and at the moment of recombination, it stood at somewhere around 400,000 light years. Nothing larger than that could have been organized by pressure, because no signal carrying pressure had had time to cross a region that big. Expansion has since stretched that same span out to roughly 500 million light years. Then the coupling broke, and the interesting part is what that did to the waves. When the electrons were captured, the photons stopped scattering and streamed away, and the pressure holding up those oscillations vanished. The fluid stopped being springy. Nothing was left to push anything back towards where it had come from, and so every wave in progress simply stopped where it stood and stayed there. Which raises the question of where, precisely, each wave happened to be standing. Waves of different lengths cycle at different rates, and they had all been running against the same clock. Consider the longest one that had time to do anything at all. It compressed once, steadily, and reached its maximum compression at the very moment the pressure disappeared. It was frozen at its densest and hottest. Now take a wave half that length. Being shorter, it cycled twice as fast, so in the same interval it compressed, rebounded, and was caught at its most rarefied, its thinnest and coolest point. A wave 1/3 the length had time to compress, rebound and compress again, and was frozen hot. 1/4 of the length, and it was frozen cold, so the sky ends up carrying a series of preferred sizes. There is a largest spot size set by the sound horizon, where the contrast between hot and cold is strongest. There is another at half that size, and another at 1/3, and another at 1/4, running down in a sequence, each one marking a wavelength that happened to be caught at an extreme of its cycle. And in between them, at the sizes that were caught mid-swing, passing through average density at full speed, neither compressed nor rarefied, there is comparatively little to see. That sequence is a harmonic series. It is the same arithmetic that governs an organ pipe or a plucked string, where a fundamental note is accompanied by overtones at halves and thirds and quarters of its wavelength, and it arises here for the same reason, a medium with a fixed size available to it, disturbed and then interrupted. The note itself was very deep. A wave 400,000 light-years long, traveling at half the speed of light, completes one full cycle in around 750,000 years. The lowest note you can hear cycles 20 times a second. This one cycled once per 750,000 years, and it was doing so in a medium light-years across, and there was nothing anywhere in existence with any structure capable of registering it. On the sky, that largest frozen wave shows up as a characteristic spot size a shade under 1 degree across, about 1.5 times the width of the full moon, which is exactly why the story had to wait. An instrument averaging everything inside a 7-degree patch cannot resolve a 1-degree feature, so the entire harmonic sequence lay below what COBE was built to see, smeared into the broad undulations it did report. Everything anyone wanted to know about the early universe, its shape, its contents, the proportions of what it was built from, sat encoded in the sizes of those frozen spots. What remained was to measure them accurately, and that turned out to be a problem of altitude. The obstacle was the air, and the cheapest way past it turned out to be a balloon. Water vapor and oxygen in the atmosphere glow in exactly the band this work requires, and they glow variably, shifting with weather and humidity and the angle you look through. A satellite escapes all of that but costs a decade and a fortune. A high-altitude balloon can carry an instrument to around 37 kilometers, above 99% of the atmosphere by mass, for a small fraction of either, and it can carry something larger and sharper than the modest radiometers that had gone up on COBE. A bigger mirror resolves finer detail. That was the entire requirement. 2 experiments got there first, and they went about it differently. Boomerang flew from Antarctica, exploiting a piece of geography. In the southern summer, the sun over the pole never sets, which keeps a balloon's temperature stable, and a ring of circulating wind runs around the continent and returns roughly to where it started. A balloon released into that current stays aloft for days and comes back to be recovered. The flight lasted about 10 days, mapping a patch of southern sky at a resolution far beyond anything achieved from space. Maxima worked from Palestine, Texas in short overnight hops, covering a smaller area of sky with a comparable instrument. The 2 teams were, in effect, racing. Both published in the year 2000 and both found the spots. What they measured at its simplest was how large the largest ones were. And that measurement on its own settles a question that had been open since the geometry of curved space was first written down. The reasoning runs through something completely familiar. Hold a meter stick at arm's length and it covers a certain angle. Move it further away and it covers less. Knowing an object's real size and measuring the angle it spans gives you its distance, or when the distance is already settled, tells you something about the space in between. The sound horizon is an object of known real size, not measured but calculated from the physics of a hot fluid with a known composition running for a known length of time, and the distance to the surface it is printed on is known as well. So the angle it ought to subtend can be worked out in advance. The complication and the point is that the answer depends on the shape of the space the light crossed to reach here. Space with positive curvature, the 3-dimensional equivalent of a sphere's surface, bends light paths towards each other, so a distant object of fixed size appears larger than flat geometry predicts. Negative curvature bends them apart, and the same object appears smaller. Flat space returns exactly the value Euclid would have given, so the spots become a test. Calculate their true size, measure the angle they cover, and the discrepancy between the two is the curvature of the universe. Boomerang placed the largest spots at around 9/10 of a degree. Maxima came in at a slightly smaller figure, and the two agreed within their uncertainties. Both sat close to the flat prediction and a long way from where either curved alternative would have put them. Taken together, the results pinned the total density of the universe to within roughly 10% of the value that makes space flat, and every measurement since has narrowed that margin without moving the answer. Then came the second question, which the sizes alone could not address: how tall each peak in the sequence stands relative to the others. Begin with ordinary matter. Adding protons and helium nuclei to that coupled fluid makes it heavier without making it appreciably stiffer, and a heavier load on a spring behaves in a specific way. It sags further on the way down than it rebounds on the way up. The oscillations become lopsided, compressions go deeper, rarefactions fall short, which shows up directly in the harmonic sequence, because the waves caught at maximum compression and the waves caught at maximum rarefaction alternate down the series. Heavier fluid means the compression peaks stand taller and the rarefaction peaks in between are suppressed. The ratio between the first peak and the second is therefore a measurement of how much ordinary matter the early universe contained. Read off a photograph of it taken before any of that matter had done anything. Dark matter announces itself differently, mostly through the third peak. Dark matter does not oscillate because pressure has no purchase on it. It simply sits in its wells, holding them open while the fluid sloshes in and out. How deep those wells were, and how much they had decayed by the time the smaller waves were ringing, depends on how much dark matter was present and how early it came to dominate. A high third peak means a great deal of it. The third peak is high. What the balloons could establish, and what everything since has confirmed with steadily better precision, is that ordinary matter, the protons and neutrons, everything on this planet is assembled from everything you have ever picked up, accounts for a small minority of the material in the universe. The rest is something that pulls but does not shine, does not scatter light, and has never been identified. At the small end, the sequence stops. The photons and the matter were never quite perfectly locked together. A photon between collisions covered a short distance, and no two photons covered exactly the same path. So across the whole opaque era, each one wandered a certain net distance sideways through the fluid. Any temperature difference on a scale smaller than that wandering distance got averaged away. Hot photons drifting into cool regions, cool ones into warm. The difference smeared out before it could be frozen. Below about 1/10 of a degree on the sky, the pattern fades out. The early universe blurred its own image, and the blur has a measurable width. One retrospective correction belongs here. The variations Kobe reported were not part of this harmonic sequence at all. They were larger than the sound horizon, which means they were bigger than anything pressure had had time to organize. And they arise instead from the plain fact that a photon climbing out of a gravitational well arrives with less energy than it started with. Deeper well, cooler photon. That effect dominates the broad end of the sky, and it is what a 7-degree beam was seeing. There is a companion to it worth noting. A photon that falls into a well and climbs out again should break even. If the well is being stretched flatter while the photon is inside it, the climb costs less than the fall paid, and the photon comes out with a small surplus. Wells get stretched flatter when the expansion of the universe starts accelerating, which makes that surplus a fingerprint of whatever is driving the acceleration. Balloons had taken this as far as balloons could take it. 10 days above Antarctica is 10 days. The sky is large, and resolving the fainter peaks further down the sequence would need years of uninterrupted observation from somewhere with no weather at all. The spacecraft built to do it carried the name of a man who had spent the winter of 1964 assembling a radiometer that was never quite finished in time. 37 years is a long time to spend on a single measurement. David Wilkinson was in his late 20s when the telephone rang in Robert Dick's office, and he was one of the 2 people in that group who had actually been building the hardware. Being beaten to a result by 50 kilometers and half a year is the kind of thing that ends some careers and redirects others. It redirected his. Roll and Wilkinson finished the radiometer anyway and published their own measurement at a different wavelength the following year, confirming from the Princeton campus what had been found in a field in Holmdel. Then Wilkinson kept going, and he kept going for the rest of his life. He worked on the balloon experiments and the ground-based experiments through the 70s and 80s. He sat on the science team for COBE. And when the case was made for a follow-up satellite, one built specifically to resolve the harmonic sequence that the balloons had only glimpsed, he helped design it. The argument for going back to space was about time rather than height. Balloons get above the atmosphere for days. A sharper picture requires collecting the same faint signal over and over until the random noise averages down, and averaging down takes years, not days. It also requires the whole sky rather than a patch of it, because the largest features on the sky are the ones that constrain the geometry most tightly, and you cannot measure a 60-degree feature through a window 10 degrees wide. The place chosen was a point about 1.5 million kilometers from Earth, directly opposite the Sun, roughly 4 times as far away as the Moon. It has a useful property. From there, the Sun, the Earth and the Moon all lie in the same direction, close together in the sky, which means a single shield can block all 3 at once. Behind that shield, an instrument sits in permanent shadow at a stable, very low temperature, with the entire opposite hemisphere of sky open to it and nothing warm anywhere in view. A satellite in low orbit, by contrast, has the Earth filling a substantial fraction of its sky and swings in and out of sunlight every 90 minutes. Getting there took a detour. The spacecraft launched from Cape Canaveral on the 30th of June, 2001, and rather than burning straight out, it spent a month working through a series of widening loops around the Earth, timed so that its final pass would bring it close to the Moon. The Moon's gravity did the rest of the work, flinging it outward to a destination 4 times more distant than the Moon itself. It settled into position around 3 months after launch. The instrument worked on the same principle as its predecessor and did it much better. 2 telescopes pointed roughly 140 degrees apart, reporting only the difference between the 2 patches they saw, while the spacecraft spun and slowly precessed so that over 6 months, every part of the sky had been compared against every other. It observed in 5 frequency bands rather than 3, spread from about 23 GHz up to 94, which gave a considerably better handle on separating out the glow of our own galaxy. Against COBE, it was roughly 45 times more sensitive and 33 times sharper. The beam came down from 7 degrees to about 1/5 of a degree, comfortably fine enough to resolve the 1-degree spots and to trace the harmonic sequence well down past the first peak into the second and the third. What comes out of that is a list of ingredients, and from the ingredients, everything else follows. An age is not something you can read off a photograph. What the peaks give you is the composition of the universe and the rate at which it is currently expanding. And once those are known, the equations governing how a universe of that composition expands can be run backwards. Given the amounts of ordinary matter, dark matter and dark energy, and given how fast things are receding now, there is exactly one history that arrives at the present state, and its length is the age. The number is calculated rather than observed, which is precisely why it is so tightly constrained. It inherits its precision from several independent measurements that all have to agree. The final results, drawn from 9 years of observation, put the age of the universe at 13.77 billion years, with an uncertainty of about 59 million. 59 million years is not a small quantity in its own right. It is nearly as long as the entire stretch since the last of the dinosaurs died. The whole rise of mammals, primates, and everything that followed, contained inside the error bar. As a fraction of the total, it comes to less than half of 1%. The expansion rate came out at around 69 kilometers per second for every 3.25 million light-years of separation. The densities of matter and energy were each determined to roughly 1.5%. There was also a stranger result buried in it. How rapidly the early universe expanded depends on how much energy was present, and neutrinos carry a share of that energy. So the shape of the peaks is quietly sensitive to how many distinct kinds of neutrino exist. The answer that came out of the sky was consistent with 3, which is the number particle accelerators have counted here on Earth. A photograph taken 380,000 years after the beginning of the universe agrees with a collider in Geneva about the roster of fundamental particles. The clearest single statement of what all this achieved is unglamorous and worth quoting anyway. The standard model of cosmology has 6 free numbers in it, and before this mission, the range of values those 6 could plausibly take defined a certain region of possibilities. Afterwards, that region was smaller by a factor of about 68,000. Spread evenly, that is roughly a 6-fold tightening on each of the 6 at once. A field in which the answers had been argued over for decades reduced, in under a decade, to a handful of numbers with error bars in the second decimal place. The spacecraft did not launch under Wilkinson's name. It went up as the Microwave Anisotropy Probe, which is what it had been called all the way through design and construction. He died on the 5th of September 2002, 14 months after it reached its station, of cancer. He was 67. The first year of results was published on the 11th of February the following year, 5 months later, and the mission was renamed for him around the same time. He had been in the room in 1965 when Dickey put down the telephone. He spent the 37 years afterwards on the same measurement, and the instrument that finally pinned down the age of the universe carries his name because he was not there to object. And while it was still gathering data, a second spacecraft was being assembled on the other side of the Atlantic, aimed at the same cold point beyond the Earth, built to reach further down the sequence than his could. For a couple of years, the coldest known object anywhere in space was a European satellite, and it had to be, because it was attempting to measure something warmer than itself. Planck launched on the 14th of May 2009 from Kourou in French Guiana, sharing an Ariane 5 with the Herschel Space Observatory. 2 spacecraft on 1 rocket, both bound for the same cold station beyond the Earth that Wilkinson's mission already occupied. It settled into position at the beginning of July. It carried 2 instruments covering 9 frequency bands, and the more sensitive of the 2 ran on detectors held at 1/10 of a degree above absolute zero. That is the whole trick. A detector at any appreciable temperature glows in the band it is trying to observe, and drowns the signal in its own warmth, so measuring a sky at 2.7 degrees requires apparatus 27 times colder than the thing you are trying to look at. The cooling chain that achieved it was the most elaborate ever flown, and it ran until the helium was exhausted in January of 2012. The resolution came out at around 1/12 of a degree, sharp enough for the first time to see past the harmonic peaks and into the region where the pattern fades out under the photon's own wandering. The results were released in stages, with the final set published from data gathered across the whole mission, and they read as a description of a universe rather than a list of measurements. The age came out at 13.797 billion years, with an uncertainty of about 23 million. Against the 59 million that had stood before, the margin had been cut to well under half. The expansion rate settled at around 67 kilometers per second for every 3.25 million light-years, a figure slightly lower than the earlier satellite had reported, and one that sits in awkward disagreement with the answer obtained by measuring nearby galaxies directly, a disagreement that has since become the most stubborn open problem in the subject. And the composition arrived with the ordinary matter separated out from the rest. Protons and neutrons, everything you have ever touched or breathed or built with, come to 4.9% of the contents of the universe. Dark matter accounts for around 27%. The remaining 68% is dark energy. That last number deserves a note about how it is obtained, because the light does not show it directly. What the peak positions establish is that space is flat, and flatness fixes the total density of the universe at one specific value. What the peak heights establish is how much of that total is matter of any kind, and the answer is roughly 31%. Dark energy's share is the shortfall. It is not detected in the photograph so much as required by it, the amount by which the universe fails to contain enough matter to be the shape it demonstrably is. There is also a measurement in there of when the darkness ended. After the first stars ignited, their ultraviolet light tore the electrons back off the hydrogen between the galaxies, and free electrons scatter light, which means a small fraction of the relic photons have been deflected a second time on their way here. That second scattering leaves traces, a slight softening of the pattern and a distinctive polarization signal at the largest angular scales, and the size of the effect indicates how much material the light passed through. Planck's figure puts the switching on somewhere around 700 million years after the beginning. The end of the long dark is written into the same photograph as the beginning of it, which leaves the question that had been sitting unanswered since the first faint ripples were found, where the pattern came from in the first place. The trouble is easiest to see by asking why the sky is so uniform. Sound could travel a certain distance in the time available before recombination, and light a little further, and beyond that distance no signal of any kind could have passed. Two patches of sky separated by more than about 2 degrees had therefore never been in contact. No influence, no exchange of heat, nothing. The sky above you contains something like 10,000 such regions, each one causally sealed off from all the others, and every one of them arrives at the same temperature to within 1 part in 100,000. Nothing in ordinary physics makes that happen. Objects reach the same temperature by exchanging energy, and these had no opportunity to exchange anything. The proposed resolution is that they did exchange energy very early, while everything now visible was packed into a region small enough to equilibrate, and that the region was then expanded violently and briefly until it was larger than everything anyone would ever be able to see. The uniformity is inherited. It was established when the whole observable universe was smaller than an atom and then stretched out along with everything else. The stretching required is not modest. To account for the sky, that patch has to grow by a factor of something like 100 trillion, and the entire episode has to be finished before the universe is a trillionth of a trillionth of a trillionth of a second old. The idea would be difficult to take seriously if it only solved that one problem. What makes it testable is a second consequence, which nobody was looking for when the mechanism was proposed. Empty space is not perfectly still. Quantum mechanics does not permit any field to sit at exactly zero everywhere. There are unavoidable fluctuations, appearing and cancelling continuously, far too small and far too fleeting to matter. Under ordinary conditions, they average themselves away. If space is expanding fast enough, they cannot. A fluctuation gets pulled apart faster than it can cancel, carried beyond the region that can communicate with itself, and stranded there as a genuine variation in density. Inflation would take the microscopic jitter of empty space and freeze it into the fabric of the universe at enormous scale. That is the claim about where the ripples came from, and the test of it lies in how their strength varies with size. If the fluctuations had identical strength on every scale, the pattern would be perfectly balanced, and the number describing that balance would be exactly 1. Inflation predicts something slightly different. The expansion during inflation has to be gradually slowing, because otherwise it never ends, which means the fluctuations frozen in earliest, the ones that become the largest features, were imprinted while the expansion was marginally faster and are marginally stronger as a result. The prediction is therefore a small excess of power at large scales, and a number just below 1 rather than exactly 1. The measured value is about 0.965. It is 3.5% below 1, and the measurement is precise enough that exactly 1 is excluded by more than 8 standard deviations. The tilt is real, it is small, and it leans in the direction the theory requires, which means the third decimal place of a number extracted from a satellite parked 1.5 million kilometers from Earth is evidence about what was happening in the first fraction of an instant of existence. And it says that the largest structures in the universe began as quantum noise in a patch of empty space smaller than a proton. All of that comes out of temperature alone, out of how warm each part of the sky is. The light carries a second channel as well, because it is faintly polarized, and there may be something in that polarization far more direct than a tilt in a spectrum. The actual imprint of gravitational waves rolling through space during inflation itself. Nobody had ever found it. In March of 2014, a team announced that they had. The people who took the claim apart were, in large part, the same people who had made it. It stood for 11 months. Understanding what was claimed and why it would have mattered so enormously requires knowing how light acquires a direction in the first place. Light is a wave, and the wave has an orientation, a plane in which it oscillates. Sunlight and lamplight arrive with those orientations jumbled at random, which is why the world only changes when you put on polarized glasses, but certain processes sort them. Reflection off a wet road sorts them, which is what polarized sunglasses exploit. Scattering sorts them too, and the relic light was scattered a great many times. A photon bouncing off a free electron comes away with a preferred orientation, but only under one condition. If the electron is sitting in a perfectly even bath of radiation, with every direction contributing equally, all the preferences cancel, and the result is unpolarized. A preference survives only if the light reaching that electron was uneven in a particular way, brighter along one axis than along the axis at right angles to it, which is exactly what happened wherever the fluid was moving. In a region flowing inward, an electron saw radiation slightly compressed and warmed from the directions it was heading into, and slightly cooler from behind. That lopsidedness, imprinted at the moment of the final scattering, comes through in the polarization of the light that got away. The temperature map records where the gas was dense. The polarization records where it was moving. Sorting those orientations across the whole sky produces a pattern, and the pattern divides cleanly into two kinds according to a single property, whether it has a handedness. The first kind is arranged radially or in rings around the hot and cold spots, with the orientations pointing either straight at the center or straight around it. Hold that pattern up to a mirror and you get back exactly what you started with. It is called an E mode, after the way electric field lines arrange themselves around a charge. The second kind swirls. The orientations wind around the spots in a consistent rotational sense, and a mirror reverses that sense, turning a clockwise pattern into a counterclockwise one. That is a B mode, named after magnetic field lines. The distinction carries an enormous amount of weight because of what can and cannot produce each type. Sound waves in a fluid push and pull along the line between compressed and rarefied regions. There is nothing rotational about that, no preferred sense of twist anywhere in the physics, and a pattern built from such flows is necessarily mirror symmetric. Density variations, no matter how complicated, can only generate E modes. That is a theorem rather than an expectation. Gravitational waves are different. A gravitational wave passing through a region stretches space along one axis while squeezing it along the perpendicular one, then reverses, and it comes in two states that are mirror images of one another. A background of such waves can leave a swirl behind. So a B-mode pattern at large angles is not merely evidence for inflation, it is the only thing that could produce one. The first half of the picture was confirmed at the South Pole. An instrument called DASI stared at two small patches of sky for 2 years, and in September of 2002 reported the detection of E-mode polarization, at a confidence corresponding to roughly 1,000,000 to 1 against a fluke. The amplitude mattered as much as the detection. The strength of the E-modes can be calculated in advance from the temperature map, since both are produced by the same density variations and the measured value landed squarely on the prediction. Nothing new was discovered. What was established was that the entire mechanism, from acoustic oscillations to scattering geometry, works exactly as described, which left the swirl, and everybody in the field went looking for it. The BICEP 2 telescope, also at the South Pole, was built for that purpose, and in March of 2014 its team called a press conference and announced a detection. The signal they reported was strong, considerably stronger than a great many models had led people to expect. Taken at face value, it was the first direct evidence of gravitational waves from inflation, a measurement of physics at energies no accelerator will ever reach, and an achievement that would have been recognized with a Nobel Prize almost immediately. Doubts were raised within days, and they were about dust. Interstellar grains are not spherical. They are elongated, and they sit in the Milky Way's magnetic field, which torques them until their long axes line up across enormous volumes of space. An aligned population of elongated grains, glowing thermally in the microwave band, emits polarized light. And because the galaxy's magnetic field is turbulent and folded rather than smooth, the pattern that results is not confined to the mirror-symmetric kind. Galactic dust produces swirls. Our own galaxy makes B-modes, and it sits between you and everything else. BICEP 2 observed at a single frequency. The technique for separating a foreground from the relic light depends on color, since the relic light is a black body with a fixed brightness ratio between any two frequencies, while dust follows entirely different rules. And with one frequency, there is no ratio to take. The team had instead relied on external estimates of how much polarized dust lay in the particular patch of sky they had chosen, and those estimates were too low. Planck released its own maps of polarized galactic dust that autumn, based on 9 frequency bands, and the patch in question turned out to be considerably dustier than assumed. On the 9th of March, 2015, a joint analysis appeared, written by the BICEP 2 team together with the Keck Array Group and the Planck collaboration, combining all 3 datasets. It found strong evidence for dust and no statistically significant evidence for gravitational waves. It is worth being precise about what that sequence represents. A claim was published with its data attached. The data allowed anybody to check it. The check was performed by a partnership between the original team and the group whose measurements contradicted them, and the correction appeared under all of their names 11 months after the announcement. In a field where a wrong result can survive for decades, that is fast, and the people who moved fastest were the ones with the most to lose. The episode also produced knowledge. The joint analysis was a better constraint on primordial gravitational waves than had existed before it, and successive measurements have tightened it further. Combining everything currently available, Planck, the South Pole Telescope, the Atacama Cosmology Telescope, the ongoing BICEP and Keck observations, whatever gravitational wave signal is present contributes less than about 3% as much power as the density variations do. Swirls have been found incidentally, just not the right ones. As the polarized light crosses billions of light years on its way to you, it passes through clumps of intervening matter whose gravity deflects it slightly, shearing the mirror-symmetric pattern and converting a small fraction of it into swirls. Those have been measured, and they are a useful probe of how matter is distributed along the way. They are also a haze lying on top of the thing everyone is actually hunting. So the imprint of inflation, if it is there at all, remains below the level anyone has yet reached, and it is not the only thing still missing. The same photograph that fixed the age of the universe and its composition and its shape has produced, in the years since, two numbers that stubbornly refuse to agree with one another, and a handful of features across the sky that nobody has been able to account for. And standing behind all of it is the oldest question in the whole subject, which is what lies on the far side of a wall built out of light. There is a disagreement in the field at the moment, and it has been getting worse rather than better, which is not how disagreements in physics normally end. The quantity in dispute is the rate at which the universe is currently expanding, and there are two ways of arriving at it that ought to give the same answer. The first runs through everything described so far. Measure the harmonic peaks, extract the composition, apply the equations that govern how a universe of that composition evolves, and run the calculation forward across 13.8 billion years to the present day. The answer that comes out is a prediction rather than an observation, the expansion rate the early universe implies for now. Combining the satellite data with the two large ground-based observatories at the South Pole and in the Atacama, that prediction sits at about 67 kilometers per second for every 3.25 million light-years, with an uncertainty under half a unit. The second way is to go and look. Find a nearby galaxy containing a type of pulsating star whose intrinsic brightness can be worked out from the rhythm of its pulsing. Use those stars to calibrate the distance, then use exploding stars of a standard brightness to extend the same measurement much further out, and compare each galaxy's distance against how fast it is receding. That chain has been under construction for a century, and the James Webb Space Telescope has now removed one of its longest-standing weaknesses by resolving individual stars in crowded fields that older instruments could only blur together. The answer the ladder gives is about 73.5. 67 and 73 do not overlap. The gap is roughly 9%, and the uncertainties on both ends are now small enough that the disagreement stands at something close to 5 standard deviations. It has widened, not narrowed, with each round of improvement. The obvious escape would be a flaw in one of the two chains, and the most promising candidate has been eliminated. It had been suggested that the pulsating stars used for calibration were contaminated by unresolved neighbors, inflating their apparent brightness and shortening the distance scale. The new observations rule that out at 7 or 8 standard deviations. Whatever is wrong, it is not that. Honesty requires one further complication, because the picture is not two tidy camps. A separate group using a different rung on the ladder, the brightness at which red giant stars reach their limit and change character, arrives at a value close to 69, comfortably nearer the early universe prediction than to its own supposed allies. The local measurements do not entirely agree with each other either. This is what a live problem looks like from the inside. Not two clean answers in opposition, but a spread, with the methods that ought to be equivalent returning results that are not. If the disagreement survives, and it has survived a decade of attempts to kill it, then something is missing from the account of what happened between the release of the light and the present day. Not from the photograph itself, which is measured to an absurd precision, but from the model used to carry it forward. That is the largest of the open problems. The others are stranger and smaller. Scattered across the map are features that nobody has been able to explain. The most discussed is a patch about 5 degrees across in the direction of the constellation Eridanus, which is roughly 70 millionths of a degree colder than average. That does not sound remarkable until you know that a typical cold region in the map runs to around 18 millionths. This one is 4 times deeper than it has any statistical right to be, And the coldness is not even the oddest part. It is ringed by a band that is correspondingly warm. A partial explanation exists. A vast, underdense region lies in roughly that direction, about a fifth emptier than average, and stretching close to 2 billion light-years. And light crossing a region that is being stretched flatter while the crossing happens arrives with slightly less energy than it started with. The same effect that makes accelerating expansion detectable at all. The void is real, and its contribution is real. It accounts for perhaps 10 or 20% of the temperature deficit. The rest is unaccounted for. There are others. The two largest scale patterns in the sky have preferred axes that lie suspiciously close together and closer than they ought to be to the plane of Earth's orbit around the Sun, which is not a direction the early universe has any business knowing about. One hemisphere carries around 7% more power than the other. The very broadest pattern of all is weaker than the model predicts, and the correlation between widely separated patches of sky largely disappears beyond about 60 degrees. What matters, and what keeps this from being an inventory of the spooky, is a piece of statistical discipline. These features were noticed first in the WMAP maps and then confirmed independently by Planck using different detectors and a different scanning strategy, so they are genuinely present in the sky rather than artifacts of one instrument. But a map contains an enormous number of things that could be looked at and examine a large enough dataset for unusual configurations, and some are guaranteed to turn up, and the significance of an oddity spotted after the fact is much harder to assess than one predicted in advance. Several of these have become less impressive as the data improved. None has an accepted explanation, and none is yet strong enough to force one. Better instruments are arriving. In the Atacama Desert, the Simons Observatory brought its large telescope to first light in March of 2025, with an array of detectors far exceeding anything previously deployed. A larger project drawing together the South Pole and Chilean efforts is proposed to follow it. A Japanese satellite designed specifically for the polarization search is working through its development phases, with a launch target in the mid-2030s. And there is a channel nobody has opened yet. The blackbody curve is perfect to 50 parts in a million, which is the limit of what has been measured rather than the limit of what is there. Any energy released into the light before it broke free, from particles decaying, from matter falling together, would leave a specific small departure from the ideal shape, and reading those departures would open a window on epochs earlier than the surface of last scattering. The instruments to do it have been designed. None has flown. One piece of the human story closed while all of this was going on. In 2019, the Nobel Prize in Physics was awarded for contributions to the understanding of the evolution of the universe, and half of it went to James Peebles for theoretical discoveries in physical cosmology. He had been the youngest person in Dicker's group, the one handed the calculations, the one who later worked out how recombination actually proceeds and built much of the framework that turns a photograph of the sky into a description of everything. 54 years passed between the letter he co-wrote and the prize. Of the 4 names on that paper, his was the last, and it was the only one still available. Which leaves the wall. It has been called a boundary throughout, and the word needs its final qualification. It is not the edge of the universe, and there is no reason to think the universe has one. It is not even, strictly, a limit on how far anything can be seen. It is a limit on how far light can carry information, and it exists for one reason only. Before it, there was no light able to travel freely, so there is nothing for a telescope to collect. The wall is made of opacity. It is the last moment at which the universe stopped scattering its own illumination. Other things were not scattered. Neutrinos barely interact with matter at all, which was demonstrated much earlier by the ones that stream straight out of the sun's core while light staggers for millennia. In the early universe, the same property had the same consequence. Neutrinos stopped interacting with everything else when the universe was about 1 second old, 380,000 years before the light got free. And they have been traveling untouched ever since, cooling with the expansion just as the photons did, and they are here now. There are roughly 300 of them in every cubic centimeter. In the volume a human body occupies, about 20 million relic neutrinos are present at any instant, at a temperature just under 2 degrees above absolute zero, carrying information from the first second of existence. Not one has ever been detected. They interact so feebly and they carry so little energy that catching a single one requires an experiment that does not yet work. A collaboration has been trying for years, using a technique that depends on neutrinos being captured by unstable atoms, and the prototypes are still prototypes. Behind them, in principle, lies something older still. Gravitational waves passing through the universe are unimpeded by anything at all, which means a background of them, if it exists, would reach back not to a second, but to a fraction of an instant. Those are the waves the polarization searchers are hunting, and they remain unfound. So the oldest light is not the oldest thing, it is the oldest thing that can currently be seen, which is a smaller claim and a more honest one. The legibility is temporary. This light has been cooling since it was released, and it has not stopped. It will go on stretching and dimming for as long as the expansion runs, and in 100 billion years it will be so faint and so cold that nothing constructed out of ordinary matter could register it. Long before then, the galaxies beyond our own small group will have been carried past the horizon, out of sight and permanently out of reach, and anything alive in that era would look up into a black sky, holding a few local stars, and find no evidence anywhere that any of this had ever occurred. There is a window during which the beginning of the universe can be read. Measured against the thing being read, it is not a wide one, and it happens to be the window we are standing in. That is worth carrying into the dark, and there is nothing to be done about it tonight. The wall around you is still there. It has been there since before there was a you to be at the center of it, and it is genuinely yours. The particular photons arriving in this room left material that now sits some 45 billion light years away in every direction at once, and no other observer anywhere shares that shell. Somebody in a galaxy on the far side of everything has their own, and theirs is made of different light. It is arriving now. It has not paused since the fog cleared, and it does not pause for weather, or for night, or for anything at all. 400 photons in every cubic centimeter of this room, and 20 million more of the older, quieter things passing through you at the same moment, none of which will ever touch anything. None of it requires attention. It arrived while the room was empty, and it will arrive while you sleep. It fell on this planet before there was a planet, and it will keep falling for a very long time after. 13.8 billion years, and it will still be arriving in the morning. Rest now. Good night.